In exercise 9.9, we have the two formulas f and g, and we have to either give a proof for a positive answer or a counter example for the negative answer. If in the first one, if f is a logical consequence of g, and whether g is a logical consequence of f. Now, by definition 9.23, f is a logical consequence of g if g implies f is valid, so if it's a tautology. Before we go into the proof or counterexample, we can maybe try to get some kind of an intuitive idea of what f and g mean, and whether it's true that f is a logical consequence of g. So if we look at g here, we have a y which is bound by the existential quantifier, and that this y is in B and in C. So essentially what g is saying is that there is at least one item which B and C have in common. Well, f on the other hand, f here we have one bound variable x in the existential quantifier here, but then we have also one free variable here. So here they're just saying that there is some element in B, but then there is some unbound y in C. So in the first one, they're asking, is it true that if B and C have some element in common, that there is some element in B and that there is at least one element in B, and that there is some other element in C. Some other but specific elements, I can say. So just think about that for a second before we go into what makes f and g true. I'm going to just bring it up and not have to have you wait for me to write it. So for f to be g under some structure M and valuation V, this needs to be true. So this is true if first, so we have an intersection here. So both B has to be true and C, or the C part, has to be true, and that's what this essentially says here. That B of x under structure M and V has to be true, and C under M and V also has to be true. Now B under M and V is true if this x under M and V is in B. So that's what requires this to be true, and the C part here is true if this y under M and V is in C. For this first part here, this means that there has to be some A in M which is in B. Like there is some A, and this y under the valuation is in C. So notice the difference here. This x here was bound under the existential quantifier. So here they're saying there has to be some A which is in B, but here they're saying that this y, whatever this y is mapped to, has to be in C for it to be true. Now for G here, for G to be true, again, the B part and the C part have to be true, so this is the same. And again, for B to be true, then this y under M and V has to be in B, and this y under structure M and V has to be in C. And this is true if for some A it's such that some A is in B and some A is in C. So notice that this is different from last time. Last time the y was free, so here we just we didn't have for some A, but here the y is bound. So both the y here in B and C are bound. So it's the same for both. The criteria for being true are the same for B and C. We just have to have some A in M such that the A is in B and the A is in C. But notice that they have an and between the B and C. So this means that the same A has to be in both B and C. So in the final line summarizes it quite well, which is that this A has to be in the intersection of B and C under the structure M. So that's the criteria for G to be true. So now let's check if it's so that f is a logical consequence of g, i.e. that g implies f is true. Now the only way for this to be false is if g is true, so that this is true, but f somehow ends up being false. Now think, is there any way that we could make this false, so that you could find some kind of a structure and evaluation such that g is true and f is false? This is the counterexample. So it's not true that f is a logical consequence of g. I mean, and the way we do that is that we come with an example. So we have this structure M, which has 5 and 6, and then we let B and G be essentially the same. They just have the element 5. So we do this because we want the G to be true. So we want to have it so that there is some element such that that element is in B and that element is in C. So that's why we have B and C the same. And then we have the assignment V, which will only have an effect on the free Y here. And then we let that Y to become a 6 under the valuation V, under the assignment V, sorry. And then we have, then this means that G implies F is not true under our structure M under the assignment V, because as I said before, this G is true because B and C have something in common, but F is not true because here B and C do not have something in common. We have let the Y be a 6, and the 6 is not in C, so the intersection of like this C and this B is the empty set. So yeah, so this implication then, since the antecedent is true and the consequent is false, is just evaluated to 0, which means that G implies F is not satisfied under the structure M, which means that G implies F is not satisfied under every structure. So that means that it's not a tautology, it's not valid. And by definition 9.23, this means that F is not a logical consequence of G. Okay, for the second part, if G is a logical consequence of F, we're going to do the exact same thing. Just take a moment here and think about it, sort of like the semantics behind it. If F is true, does it mean that G necessarily is true? So it is not true that if G is true, that G is true. So G is not a logical consequence of F. We can think about this. If there is some element in B and some other specific elements, no, if there exists at least one element in B and there is some other element in C, this does not mean that B and C necessarily have at least one element in common. So we're going to let the structure M be the same as last time. We have 5 and 6, and then here, however, we're not going to let B and C be the same because we want this G to be false. Remember, we want to come with a counterexample. So we're going to let the B be just the set with 5, and C be 6, be the set with 6. It's supposed to be sets here, so sets. Then let's the assignments be the same as last time. So we assign Y to 6. And then we end up with F implies G not being satisfied under our M and V here because the F is true. So we have, there is some elements in B, so the 5 is in B, and our Y, which has been mapped to 6, is in C. So both B and C are true, which is the criteria for F to be true. Remember here we had, where were we? Yep. So for F to be true, this had to be true, and this had to be true. But G is false because the intersection of B and C is the empty set. So B and C don't have anything in common. Look here, B has a 5 and C has a 6. They don't have anything in common, which implies that the evaluation of F implies G is false. Since this is false under our structure M, then it is not true. Yeah, since this is false or not satisfiable under our structure M, it is not true that F implies G is satisfiable under all structures, which means that it's not a tautology, it's not valid, and therefore, by definition 9.2 again, it means that G is not a logical consequence of F.